Hello, welcome to the
Hello.
stream.
Hello. Am I audible?
Yes.
Well, we are of course still waiting for many others to join. Hopefully.
I just want to check: is there any echo from my side at all? If you
No.
speak, that's good.
Yes, what we will ask everyone switch to go mute.
And you should tell them, Andre, that we're planning to record this. So anyone that speaks or puts their video on potentially.
Well, I did send email to everybody saying that it will be recorded and streamed. So it was
Okay, great.
Hello, everybody.
So
More people joining. Hello, just waiting for others to join.
hello, Carl. Hello, everyone.
We're still waiting for others to join. We'll begin in a few minutes. Hi everybody, we are still waiting for more people to join. We'll begin in a couple of minutes. We give it a couple of more minutes for others to join. Maybe more people are joining.
Right, there you go. Have you got left?
Hello everybody, we're still waiting maybe a couple of minutes to give a chance to join. Maybe.
And just just want to say that we recording this session, and it will be also posted on YouTube. So you will receive your link and you can share with your friends and just enjoy memory later. Before we start, we just wait for maybe 1 more minute if somebody comes. Could you please put in the chat that you can hear you can hear all the sound okay? So You can put some symbol there that you can hear.
Đấy, được rồi, ngồi thẳng lên.
So just I tell to those who arrived right now that this session is being recorded. So you will receive a link of YouTube link when you can show to your friends and just look yourself. Yes, you will have this link we send you by email. I think we can start. Right, so my name is Andrzej Zwelendowski. I'm professor and head of School of Mathematics and Physics, which conducts annual Lincoln Mathematics Challenge. And I'm joined today by chair of Lincoln's Mathematics Challenge Committee, professor of pure mathematics, Evgeny Khukhro. So Evgeny can wave and you can see him. So after we announce the winners, we'll try to wave each other and clap. Then Evgeny will give a short lecture on algebra, which is subject of his work and research, and he is author of textbooks in algebra, so an editor of journals. So you all welcome to listen, and also you might want to ask any questions, so you can put them in a chat on that how it will go. Right, so just a couple of more people arrived just now, so I just still say to everyone that we record this session, and it will be on YouTube, and you will have a link on YouTube where you can show to your friends and family. And with that, we start. So if just kind of to double check that the sound is still okay, would you mind to put any smile or thumbs up in the chat that be sure that all goes fine? Yep, okay. So let me share with you my screen. Thank you. Very good. Okay, so I'll give you a short presentation. Again, I'm Professor Andrzej Zwelendowski, very long surname, and I'm head of School of Mathematics and Physics, University of Lincoln. Because traditionally this type of award ceremony happens live when you come to city of Lincoln and can have a chance to see city, see university, and enjoy your visit. This time is all virtual. Some of you might know where Lincoln is. Maybe you visited. Some of you actually study in city of Lincoln, but some are very far away. So I thought a couple of words where we are, who we are, will be good for everyone. So University of Lincoln is located in a heart of city of Lincoln, and what you see on the screen now is actually our campus at night. We are quite small city, about 100,000 inhabitants, but the city quite old. It was founded very few years after conquest of British Isle by Romans in 48 AD, and already in 71 it was base of famous Legion number 9, Hispania, that legion which kind of vanished from history records later on, and no one quite know what really happened to that. Very early, just in 86, the city received a very prestigious status of colonia in the times of Emperor Domitian. And Lincoln is short from Lindum Colonia. This is where name comes from, as colonia that was place for instance, retired legionnaires. So it was quite comfortable place to live in already Roman times. Some of Roman remains you still can see in a city if you visit us. What you have now an image is the only Roman gate through which still traffic is allowed in whole British Isles. So you can even drive under this Roman gate. And the heart of history goes in Middle Ages. So there was times when city was in decline after Romans withdrew from Isles, but in Middle Ages was the next big step. That was already after William the Conqueror, who ordered to build a castle, Lincoln Castle, which is just opposite to Lincoln Cathedral, which he also asked. And one of the first bishops was Bishop Reminius. This cathedral is indeed considered to be quite special. Famous Victorian scientist and thinker John Ruskin considers one of best, if not the best, piece of Renaissance architecture on British Isles. So if you come to visit city of Lincoln, spend your time to see, of course, this cathedral. As cathedral was not just a place for worship, but also a place for study already in Middle Ages, and it has considerable library, medieval library of cathedral. Some of the books can be still seen in quite substantial collection. And also you will find that sometimes there is a piece of paper saying that that particular volume is on loan to University of Cambridge, for instance, for already a couple of 100 years. As a seat of bishops, and as I said, it also was a seat of learning, but never was any university till modern days. So some call what was in the city of Lincoln so-called embryo university. There was a schools, so-called cathedral schools, ready from 12th century, and one name is associated with William de Montibus. And later on, in 13th century and end of 12th century, big English thinker, Bishop of Lincoln, Robert Grosseteste, wrote several books which all survived, and they considered to be like first science, in fact physics in particular, books and cosmology written on British Isles. While there was no university in city of Lincoln, nowadays everyone kind of might know that in famous University of Oxford there is Lincoln College, and that was not because of city of Lincoln, but because of bishops of Lincoln who donated money, and they opened college in University of Oxford. And in fact, the bishops of Lincoln, including Robert Grosseteste, were teaching in University of Oxford while their kind of main job was in the city of Lincoln. And that situation only changed in already 20th century. Then university, very modern university, was opened, and in fact campus in Lincoln was opened by Her Majesty the Queen herself in 1996. And again, this is, you see the campus, and the building on the waterfront was the very same building which Her Majesty did open. That building is a home of our School of Mathematics and Physics, which is one of the newest schools in the whole United Kingdom. It opened in 2014, and we have our own building named after Isaac Newton, also from Lincolnshire. That building is open in 2017. This is where we are. We're in the center of city. If you happen to visit, you can see the old medieval city, but also come and see us on the campus, and just come and say hello. Right, so that was
Andrei, you are muted. Andrei, you are muted. Yeah.
sorry, I think I was on mute. Did you hear some of my introduction?
Nothing after the historic lecture.
Loud and clear? Okay. Now, main purpose of this meeting is presenting awards. Okay, so this is our main part of the program, where we announce the winners, and I again emphasize that YouTube receive a link. And I also again say that if you Lincoln before, when this pandemic is over, we again allowed to travel, please do come and enjoy seeing City of Lincoln. These challenges, and hope you enjoy from the challenge in 2021. Okay, I also should apologize that as a non-native speaker, I might pronounce names like they should be. So that I'll try to pronounce names, but again, I might make mistakes, so I apologize for that. Problems which we gave a challenge, been quite challenging, and competition. We received works of level, very good works, and it was not find, one winner in each category because many equally. So what we have therefore, we have several awards of each category. Simply because many of you wrote really very, very strong works, and the committee to distinguish for several places.
Andre, sorry to interrupt.
Third place.
But your voice is breaking up. Could you maybe turn off your video?
Of Link Challenge 2020. First, third place now from prior SST.
Sorry, Andre, we can't hear you.
The next, third place winner goes to Makafui Avevo, King's Edward VI Grammar School in the next place goes to from King James School. Congratulations, Nan. One more, third place goes to Adrian Petrov, Loughborough Grammar School. Congratulations again with third place. Third place is Chan from Queen Elizabeth. Congratulations. Next, third place winner is James Warrington from Sirius Academy in Hull. Congratulations. Now we go next, second place winners. We also have several in this category again because competition was really, really tough. We've got very nice works and based of the second place 2020, 2021. First, second place winner is Jack Chambers from Gordon's College in Aberdeen. Congratulations. Next, second winner from Masonic Girls, Eric. Our second place winner is Michaels Osmans from Grantham. Congratulations, Michaels. One second place winner is Jack. Just a second. And there was an interruption. Apologies, was a small interruption on my file. Could you hear me now?
It was breaking up, Andre.
And now is sound coming?
Maybe it's better.
Okay, apologies for that. I'll continue with presentation of words. If there is still sound coming from my side. Okay. Okay, thank you. I will announce second place winners again because sound seems interrupted. And when I present the winners, I actually don't see the chart. So that was the problem. The second place winner, I'll announce again. Somebody maybe not heard. So Jack Chambers received second place from Roberts Gordon College in Aberdeen. Also second place is Miranda Kohn from Royal Masonic Schools for Girls in Rickmansworth. Another second place is Michaels Kosmans from King's School in Grantham. And the following second place winner is Jack Sachs from Greenhead College, Huddersfield. Another second place winner is Anuja Sribhavananthan from William Perkins Church of England High School in Greenfield. Congratulations, Anuja. Next, second place winner is Ben Watkins from Royal Grammar School in Guildford. Congratulations, Ben. And we arrive to our final category, which is first place winners of Lincoln Mathematics Challenge 2020-2021. Again, competition was very, very strong, so we did not find a single winner, and there are a couple of winners, and therefore we will split the award between those who win the first place in this year's challenge. And those are the first place winner in Lincoln Mathematics Challenge of this year is Daoi Chen from Binkamp College, Oudbe. And next, first place winner is Trung An Nguyen from Brackenhurst College. Congratulations. That is end of our awards. Right, So now you can unmute yourself and then we try to clap. So can you try to unmute yourself?
Shall we? Yes.
Well, I'd like to congratulate my guy David Chen. I'm very proud of my guy David Chen, of course. Very proud of my guy.
Wave each other on the screen. You can
Very proud of my friend.
On the screen. Wave and congratulate each other. It's all this bit new type of ceremony online. Okay, with that, I'll finish my part and then we go to second part. So many congratulations. Again, you can, let's kind of, you put your camera, we can wave each other. Congratulations to everyone. Very well done.
Hello, guys.
If you can put your camera on, then you can see in a large gallery preview many faces, and we all far away from each other. Still, we are together in this world connected with internet. Many congratulations. Well done. We hope you enjoyed solving the problems. And just as a small treat, now we will give a short lecture on algebra. It will be maybe a little bit different algebra like you know it, but I hope you can still enjoy it. I'll be giving now a microphone to Professor Evgeny Khukhro, who is chair of Lincoln Mathematics Committee. And thanks to Evgeny and his work, you did enjoy those problems which you've been solving. Every year, Evgeny chairs the work to prepare challenging problems, and we hope you like it to solving them. So now Evgeny will give his talk on algebra, and I hope you enjoy. And you can, if you would like, you can put a question in a chat which Evgeny can answer after his talk. Okay, let's enjoy a little bit of algebra now.
Okay, before I begin my lecture, I just want to repeat what Andrei was probably saying, but we didn't quite hear. That the competition was very stiff. It was really difficult to discern the winners, and this is why we chose to award several third-place winners, several second-place winners, and we even had to split the first-place winner, as you saw in the ceremony. But now let me open the screen with my lecture, and hopefully you'll see it now on the screen, right? Okay, this is the lecture on the role of algebra in mathematics, and I will touch upon some elementary problems, but also maybe give a glimpse of some modern research in algebra that we do in Lincoln. And I begin with a very elementary problem which really belongs to primary school mathematics. And this is some curious incident which really happened to me quite a long time ago. It happened on a small railway station in the middle of Russia, where myself and my wife were waiting for a train. And suddenly a fellow passenger approached us, and he offered a mathematical problem to solve. He asked us, "Can you solve this problem? A farmer keeps chickens and pigs. Altogether, there are 100 heads and 288 legs. How many of each kind?" but he insisted, can you solve it without x's and y's? So without algebra. This is interesting why he would insist on not using algebra. And of course, the answer is that algebra makes it easier. Well, in this curious incident, he had no chance of embarrassing me, because in fact, I have just obtained my PhD in algebra, and moreover, I participated in organizing mathematics competitions, mathematics Olympiads, not unlike we just had in Lincoln. And I also have been taking part in these competitions when I was a schoolboy myself. And it just so happened that I knew this particular problem from early on. I was about 12 years old when I first saw this type of problem, and we did not really learn using algebra, learning x's and y's until later. So this guy really had no chance of embarrassing me. And here is an algebra-free solution that I immediately produced to his disappointment. Here is a solution without x's and y's. We simply assume that every animal has 4 legs, kind of attaching additional 2 legs to each chicken. Then, of course, there will be 400 legs, because we have 400 animals having 4 legs each. So we know how many extra legs we added. We added 2 legs to each chicken, so we divide by 2, obtain the number of chickens. And of course, we also have the number of pigs. The same problem can, of course, be solved with x's and y's, with algebra. It's natural to introduce these variables. X is the number of pigs, y the number of chickens. And then we shall have these equations. X plus y is 100, and 4x plus 2y is 288. Then, of course, it's easy to solve. You express y from the first equation, substitute into the second, expand brackets, collect terms, balance, solve, and you get the result. So you see the difference without algebra and with algebra. And algebra in this second solution simply means using letters, symbols for unknowns, and then solving equations becomes almost mechanical. In more advanced terms, you can even write these simultaneous equations by using matrices, like this. And of course, algebra gives algorithms, methods for solving any type of linear simultaneous equations, not just with 2 variables, of many equations. In this case, it's just a square invertible matrix. You can multiply by the inverse matrix on the left and get the answer immediately. So what's the difference? Solving with algebra may be kind of less interesting, less fun. You don't need to invent this procedure of attaching extra legs. But on the other hand, using x's and y's made this challenging problem easier. Another example is about geometry and using algebra in geometrical problems. For many years, geometry textbooks were close to the famous Elements of Euclid. And this was so-called synthetic geometry as opposed to coordinate geometry. This geometry book by Euclid was based on axioms and deriving properties of geometrical figures by using those axioms and theorems and lemmas. Nowadays, synthetic geometry all but disappeared from school curriculum, and often problems are solved with calculations in coordinates and with applications of Pythagoras or cosine theorems. Actually, when we ask students, many students do not have recollection of proofs of geometrical theorems or proof of the Pythagoras theorem, for example, although a proof is actually a part of his stage 3 curriculum. Here is one example of the difference between synthetic and coordinate geometry. This is a well-known geometric fact, a theorem that if you have a bisector of an angle in a triangle, then it divides the opposite side proportional to the lengths of the sides between which this bisector is constructed. So here ABC is a triangle, AL is the bisector of the angle A, and the theorem says that the ratio of these lengths, BL to CL, is the same as AB to AC. So a synthetic proof goes like this. One of possible proofs, you construct a line parallel to AC through this point B. And then you extend the bisector AL to the intersection with this parallel line at point M. Then we have known properties of angles for these parallel lines. We have equal angles here and here, as well as here and here. So we shall have angle MAB equal to angle MAC, and this is equal to angle BMA. This will make this triangle ABM an isosceles triangle because it has equal angles here and here. And so AB is equal to BM. And also these two triangles, BLM and ALC, are similar because of these angles. So for similar triangles, we know these are the same. So we simply write BL to CL is the same as MB to AC, and MB is the same as AB. So we obtain the required result. But this can also be achieved by using coordinates, by using equations. In this kind of algebraic proof, we simply introduce coordinates of all these points, putting A maybe at the origin, B has coordinates UV, C is on the x-axis with coordinates W0, for example. Then a point on this line is with coordinates like this, where x is a certain coefficient, an unknown coefficient, and to achieve the required proportion, we simply need x to be equal to this ratio, W over W plus root of U squared plus V squared. So this is what we need to prove the theorem, and what is given to us is the equality of these angles, because AL is the bisector. This can be expressed in coordinates by using dot product. Dot product of two vectors is simply product of the lengths times the cosine. So we can simply translate this condition that this is a bisector by writing this equation for the cosines of these angles. There are known formulas for dot product in coordinates, so we write these equations, which do not look very pretty, but quite straightforward nevertheless. And you can simply solve this equation for x. Once you do this, you really, in a straightforward manner, obtain the required result, thus solving this problem. Problem solves itself once you translate everything into coordinates. Well, the coordinate method actually arrived in geometry only in 17th century, and the name which is associated with coordinate geometry is René Descartes, and that's what we now know as Cartesian coordinates. Cartesian for Descartes. There is a legend that Descartes boasted, "I solved all geometric problems because of this method of translating into equations." In fact, it was a really big change. Before advent of algebra into geometry, in fact, geometry was used as a base for proofs, as a kind of touchstone for the rigor in the proofs. For example, the original work of Isaac Newton, if you read his works on beginning of calculus, you see that he uses geometry as ultimate proofs, rigorous proofs for his statements. But after this revolution, it was now algebra that became basis for proofs, both for calculus and for geometry. Another geometric example is about constructions with compass and straight edge. Of course, these are idealized constructions. Simply means that we are allowed to construct straight lines through two known points. We are allowed to construct circles centered at known points of known radius. Known radius means that we should be given two known points. And we are also allowed to construct intersections of these elements. These are the restrictions of geometric constructions with compass and straight edge. Some of these tasks are easy enough, like dissecting a segment. You can do with straight edge and compass, or constructing a bisect of an angle is not so difficult. But some of these problems are quite difficult. For example, the famous Apollonian Circle, it was an example of a difficult problem to be solved by using straight edge and compass, which consists simply that you are given three circles on the plane and you are required to construct a circle which is tangent to all three given circles. Well, it's possible, but it's a difficult and not so easy to do. The known method to me is using the so-called inversion transformation. But anyway, there is an algebraic approach. What you can do, you can choose, fix some segment of length, declare a segment of length 1. And then all distances become numbers. Or alternatively, you simply choose a Cartesian coordinate system. And then the constructions by straight edge and compass can be used to do arithmetic operations on these distances. Of course, it's quite easy to construct the sum. If you have two segments of length A and B, you can easily construct A plus B, A minus B. Using similar triangles, parallel lines, you can construct A times B in this configuration, or B over A in this configuration, using this fixed segment of length 1. Moreover, you can also take square roots of some lengths. If you put a segment of length A plus segment of length 1 as the diameter of a semicircle, construct this triangle, the height will have length root of A. And in this way, all possible construction problems can be solved. Simply calculate the requisite lengths, the lengths which you need for these constructions, then simply solve those equations and perform these arithmetic operations by compass and straight edge. Like that, difficult Apollonian circles can also be solved in this way. There were three famous construction problems in the history of geometry. They go back to ancient Greece, I suppose. So the questions were use only compass and straight edge to square a circle, to construct a square of the same area as a given circle. Another problem was to double a cube. Yet another problem was to trisect an angle by using straight edge and compass. And for centuries, geometers tried in vain to come up with a solution of these problems. Squaring a circle even became part of the English language as a synonym for something very difficult or even impossible. And it was indeed in the 19th century when algebra was developed enough to give an answer. The answer is that all these three construction problems are unsolvable. It's impossible to do in general. And the proof is based on algebra, is based on coordinate interpretation and also properties of algebraic field extensions. Well, to be precise, if you look at the equations of the straight lines which we are allowed to construct through given points, or the equation of circle of a given radius centered at a given point, we know these equations. And when we are solving these simultaneous equations, it means that we are finding the intersection points. So finding intersection points is simply solving simultaneous equations. And from the form of these equations, we see that all solutions are always given by quadratic equations in x and y, or linear equations with coefficients composed of known coordinates, of known quantities. So here comes algebra of field extensions. So when you are solving a quadratic equation, you are actually extending the field, building a quadratic extension of the field. We can say that we start with rational numbers, then if we construct a point which is not a rational number, if we add a number which is not a rational but a root of quadratic polynomial, we are constructing an extension of the field. Well, I do not really have time to give precise definitions, but roughly speaking, every time we have a bigger vector space, every field extension can be regarded as a vector space over the smallest field, and extensions by roots of quadratic equations means that every time the degree is 2. Degree is simply the dimension of the field over the smaller field. And the theorem in algebra tells us that the resulting dimension is always the product of these individual dimensions. So whatever we do, there is every time the field we construct must have dimension power of 2, because it will always be the product of several factors equal to 2. All extensions are quadratic, and therefore the only field extension we can build must have dimension 2 to the n over q. Now we can see why doubling a cube is impossible. If the given cube has side length 1, the volume is 1. If we want to double the volume, we must construct a side cubic root of 2. But adjoining cubic root of 2 to to rational numbers makes an extension of degree 3, because x cubed minus 2 is an irreducible polynomial over Q. This is again some facts from algebra which we simply mention here without proof. I can't really go into much more detail. So now if we assume that cubic root of 2 can be constructed in this way, after several constructions by a straight edge and compass, it will mean that cubic root of 2 will be contained in such an extension of degree 2 to the n. So we shall have this tower of fields, and this extension has degree 3, so the resulting degree must be divisible by 3. But we know it is actually 2 to the n. This is a contradiction. 3 does not divide 2 to the n, which shows that indeed doubling the cube is impossible in constructions with straight edge and compass. Similar proof is for trisecting an angle, because again there should be adjoining some root cubic of an equation of degree 3 when you write an equation for the cosine, and this is impossible in general, as we saw above. Squaring the circle is impossible because pi or root of pi is not even a root of any polynomial. This is a more difficult theorem, but nevertheless this is true. This is not even an algebraic number, and therefore this is why squaring the circle is impossible. One more, a little more advanced application of linear algebra to the so-called Euler's rotation theory. It says that any displacement of a rigid body, a sphere, in 3D with a fixed point at the center must be a rotation about some axis. However you move this sphere around this center, in the end it will always be equivalent to a rotation about some axis. There is a geometric proof of it. It's quite beautiful. You use some reflection first, then another reflection to superpose the points of this sphere, and the composite of two reflections is a rotation, and the theorem is proved. If we consider the case when the orientation is not changed. If orientation is changed, you also need another reflection. But here is an algebraic proof. In algebraic terminology, a displacement of a rigid body is described by orthogonal linear transformation. So we are simply mapping every vector to the product of this vector by a 3×3 orthogonal matrix. So what does it mean to be a rotation about an axis? It means there must be a fixed vector. So theorem really says that there must be some vector which is left unchanged by this transformation. This will be the vector of the axis about which this rotation happens. And this is indeed a consequence of the properties of orthogonal matrices. Because an orthogonal matrix with determinant 1, if orientation is not changed, must necessarily have a real eigenvalue 1. So this is where algebra gives an answer. 1 is necessarily a root of this equation, determinant of t minus lambda I equal to 0. So what is the advantage of algebraic proof? The advantage is that there is no need in geometric imagination. You're working with matrices, you are applying properties of matrices, and this type of argument will work just as well in higher dimensions. In dimensions 4 or 5 or higher, it would be much more difficult to use geometric imagination. Well, these were some examples, but now let's just draw some conclusions that algebraic theories are really abstractions of certain algebraic structures in various parts of mathematics. Algebraic objects are kind of hidden in other mathematical theories. They're kind of skeletons reflecting certain essential formal rules. You can even draw this type of proportion. Just like mathematics reflects some essential skeletal properties of scientific theories, so you can say that algebra has the same relation to other parts of mathematics. One such abstraction is abstract group theory. To give you an idea of what an abstract group theory is, let's look at transformations of a square as a rigid figure. There are, of course, 4 rotations about the center and 4 reflections. Rotation including through zero angle, which means identity transformation. So these 8 elements form the so-called group of isometries of the square. In this group, there is an operation, kind of multiplication, when you simply do one transformation after another. The product of G and H is simply doing them consecutively. So we have a group of isometries of a square consisting of these rotations, identity, transformation, rotation, another rotation, and reflections. And you can actually compute that the product BA is equal to A cubed B. And here is the kind of light bulb moment. The abstract group appears when we forget the square, forget the transformations, and we simply work with this abstract group consisting of these 8 elements subject to these rules, to these defining relations for the operation in this group. Even in this lecture, we see that algebra underlies, gives algebraic structure to many things in mathematics, like linear algebra matrices, linear systems of equations, where behind these heads and legs problems simulates applied in differential equations, or in these orthogonal transformations in Euler rotation theory, and in many other parts. Particular group theory, the notions of subgroups, quotients, multiplicators, they are the language in which we can discuss permutations of roots of polynomials, symmetries, rotations in geometry, or for example, even Rubik's cube has its own group of symmetries. And in physics, elementary particles are sometimes considered using group theory language. Group theory itself, it studies groups in their own right. And group theory is a strong point of algebraic research in our Lincoln School of Mathematics and Physics, which was founded not so long ago in 2014. And just to give you some example of recent research of what kind of algebraic research is conducted by us, I will need a couple of definitions just to give a flavor of of this recent research, although of course I will not be able to go into too much detail. One of the aspects of research in group theory is about commutativity. We actually saw that groups are not necessarily commutative. In that group of symmetries of the square, BA was not AB, it was actually A cubed B. But if we have this commutativity, this is a very good property. And commutative groups are much easier to study, and therefore getting kind of more commutativity is a very good thing, very desirable. And this is actually one of the aspects of my own research about obtaining kind of greater degree of commutativity of the group. And to give at least some explanation of what degree of commutativity we are talking about, we have to introduce some definitions. And this is a kind of measure of non-commutativity. Two elements of a group, we define this product A inverse, B inverse, AB. This is called the commutator of AB, and it's kind of easy to see that this commutator is trivial, equal to the identity element, exactly when these elements commute. Because of course, if they commute, you can rearrange and get identity element. And the other way around as well works. So we can define some non-commutative groups, but which may be close to commutative to some degree, to some extent. And this is defined using this notion of commutators. One example is actually quite important and historical as well, about soluble groups. For example, if you simply iterate and take commutators of commutators, you can define soluble groups, for example, of derived length 2. When simply a commutator of two commutators is always identity element. If you simply iterate this further, you will get definition of soluble groups of derived length k for every positive integer k. Historically, groups in general actually appeared in Galois theory. It was another century-old problem of finding formulas to solve equations by radicals. And it turned out that there is a group of permutations of roots, and the equation is soluble by radicals exactly when this group is soluble, as we just defined in the previous slide. The very term soluble group comes from this solubility by radicals. And by the way, there are non-soluble groups, and there are equations of degree 5 even, where the group is non-soluble, and therefore such equations do not have, their roots cannot be expressed by radicals. This is what was discovered in the 19th century. But let's return to my research interests, and in particular, there is another way of defining, of iterating commutators and defining another class of groups which are close to commutative. Here we simply take commutator with another element, and then with another element, and so on. This defines an important group of certain class C. Important groups are also non-commutative, but kind of closer to commutative than soluble groups. So now I can just show you some recent paper, relatively recent paper of myself, where this high abstraction is present, where the groups are in question are limits of finite groups, and commutativity type conditions are explored in this recent research paper. If you look at the abstract, you can see this notation for commutators, which is used to define certain conditions. You can see that the conclusion is about nilpotency here. So this is just an example of very recent research paper of mine. Well, concluding this lecture, I would like to say kind of thank you to the algebra. Many algebraic structures arise as abstractions from various mathematical objects and theories. And once we have these abstractions, once we develop algebra, then there is kind of payback, benefits. Algebra makes these theories and objects more transparent, provides answers, techniques, and insights. As Jean de Laberge said, algebra is generous. She often gives more than is asked for. Thank you. This is the end of my lecture.
Thank you very much, Evgeny. So if somebody has some question, you can put in a chat, or even you can raise your hand, and then you can just ask whatever you want to ask.
Anyway, I can only add that
It also could be it was quite a long day already for you, and with extra class on algebra. There is a question. So Evgeny, you see in the chat?
Yes, I see. Yes, as usual, we shall publish both the list of winners and the solutions of the problems at some point, maybe next week, on one of our websites. And I will actually send everybody the links to this site, and so you will have a chance to see the solutions and also all this. And also these certificates which Andrei was demonstrating in his part, we shall be also sending by email for you to have as, unfortunately we did not have you in Lincoln, but at least you will have these certificates sent by email. Applications of nilpotent groups in mathematics. Well, nilpotent groups play a big part in group theory itself. And I think its main applications of nilpotent groups are in group theory. And then, of course, group theory has applications in other parts of mathematics. Groups simply play the role of classification tool. Almost every part of mathematics has its own group of symmetries. Symmetries are understood in very general setting. It's not just reflection symmetries, but any transformations preserving the structure. So every part of mathematics has its own group of transformations, and therefore group theory is really everywhere in mathematics. Even in physics, as I mentioned, in physics they also like symmetries of the particles, and they use groups to describe them. And then, of course, groups simply play the role of a language, which these symmetries are described.
There are more questions.
Mathematics books or problems to recommend. Well, of course, there are some very good books. There are books. There is a famous book by Polya, for example, How to Solve a Problem. But in particular, especially for you as participants of the challenge, you can try to find collections of problems for Olympiads. For example, there must be some publications for problems of the International Mathematics Olympiads. And also the British Mathematical Olympiad is conducted every year. You may know this or not, but they surely also publish some lists of problems. And in a sense, these problems, although they are usually elementary, it's usually a requirement for these Olympiads not to use any advanced theories. But I can tell you that these problems for Olympiads are really interesting in the sense that they're really close to actual mathematical research. They're really, the mathematicians who work in mathematics, they are really solving this type of problems, albeit in more advanced settings, maybe more definitions and so on, but essentially it's the same kind of thinking. You have to invent things, you have to uncover interesting connections, and this is all present in these mathematics Olympiads. It's already there. All these challenges are really very, very relevant to actual mathematics, which is actual mathematical research, modern research. But of course, for advanced research, you need to study, you need to go very far along the way, and yeah. But the difficulty is already there. It's already the same ingenuity which is you are being trained in. Yeah. Some people ask, are there other competitions similar to this? Well, of course, we cannot really comment on other universities. I suppose that other universities also conduct this type of challenges, but there is also more centralized British mathematical competition, and unfortunately not all schools take part, but of course it would be nice if all schools would be taking part, and you can find this. I think it's possible to find online this information about British Mathematical Olympiad, because they also conduct challenges. They conduct in several stages. Of course, there is the pinnacle of this Olympiad is the team of Great Britain to the International Mathematical Olympiad, but there are also initial stages which also are interesting, and they also sometimes conduct summer schools, some camps, mathematical camps, where it's interesting to participate.
There is also a raised hand by Abdullah Al-Hidaba, so maybe you can unmute yourself and ask your question. Also raised hand, but
well,
yeah. Sorry, I was just about to ask the same thing. If there were any other competitions, I can.
Actually, one of the participants is actually answering this question even better than me. Try UK Mathematics Trust. Yes, Mathematics Trust, the name website. There is a website. If you look in this chat, you will see
I see.
Answering even better than I did.
All right, thank you.
UK Mathematics Trust, yes.
Thank you.
Okay, I just want to thank everybody for participation in this year's challenge.
Any more questions from anybody?
We were really
Maybe
pleased to have a very strong
there is
competition.
somebody. Somebody raise hand. Imran Ahmed.
I just wanted to ask, you said you did your PhD in algebra, and I was just wondering, what does a PhD in maths, what does that entail? What do you do? I'm interested.
You have to, usually PhD in mathematics involves obtaining new mathematical results. So you have to, quite often you invent your own theorem and you prove it yourself, so to speak. And so in mathematics, research is always cutting edge research. It's never repeating something. You need to invent a new theorem. You need to put forward a new theory, and you prove yourself your own theorems, so to speak. Quite often there are some even collections of unsolved problems. For example, I am one of the editors of the collection of unsolved problems in group theory. And we have many mathematicians all over the world submitting these problems. And so there are hundreds of unsolved problems. And by the way, this is one of the misconceptions. Of course, maybe not participants of this challenge, but many people sometimes think that mathematics is kind of finished. It's already something achieved long ago, but it's nothing can be further from the truth, because mathematics knowledge, as any other knowledge, I suppose, is more like an island. You have a vast ocean of unknown, and the more you know, the longer the shoreline, the more directions of further research. It never stops. There are even mathematical theorems which tell us that, for example, there is a theorem saying that you can never have, there is no algorithmic solution for all problems in finite group theory, for example. And it actually means that at any moment in time, there will always be an unsolved problem. So it's a mathematical proof that you cannot really have all knowledge already there.
Thanks for answering that.
What attracted you to group theory? Somebody asks. Quite often you begin doing what you do better, you know. You can ask first what attracted me to mathematics. When I was a schoolboy, I took part in some competitions in geography, geology, chemistry, and physics, and it turned out that my mathematics results were better. And this is quite often it's a reason why you go into something, because this is what you are good at and you enjoy it. And yeah. And group theory in particular, we had a very good teachers when I was studying in my last years at school. I was studying at the so-called specialized physics mathematics school, and our teachers were actually researchers from Novosibirsk University. And one of my teachers was actually a specialist in group theory, so he took the opportunity, took advantage of myself and my classmate Alexander Borovik, by the way. He's also professor of mathematics in Manchester now, and we both were in his class, and he kind of took advantage of being our teacher, gave us some interesting problems, and so we were hooked because these were very interesting, very nice problems in finite group theory. How does someone become a professor? Well, competition is very stiff. You have to be better than others, I suppose. You have to be devoted. Well, of course, when you start, you are not a professor, you are a young researcher, you get rather low salary, and you try hard to write papers you. Then you kind of grow through the ranks. I guess it's not much different from other fields.
I think our time is now approaching to the end of the ceremony, and maybe at the very end we still kind of try virtually. If you would like to put your camera and then we wave to each other, just to kind of celebrate the end of this event. And we, of course, here from Lincoln wish you all good luck with all your mathematics and any other studies. We hope you will love mathematics for all the rest of your lives and enjoy it.
Okay.
Thank you. Bye.
Thanks, guys. Have a safe drive home. Bye. Thank you.
Thank you very much for coming to this event of celebrating Lincoln Mathematics Challenge winners. Again, well done. Fantastic that you put so much effort in solving these problems, which were not really easy problems to solve. So we've been so happy to see your works. And I hope you enjoyed a little bit this virtual event. As I said, one day, hopefully very soon, pandemic is over. Please do come, visit Lincoln, see how this city looks like. Even if you've seen this city, still come, pass by university, say us hello. We are here in the center, very easy to reach. Thank you very much for coming. Thank you. And bye-bye. Goodbye.
Bye.
Thank you. Bye.
Have a good day, Bossman.